Okay, number 6. So, as I said a little while ago, the best choice is going to turn out to be to loop around the top half of the picture. Now, if you don't immediately spot that, as I said the other day, sometimes you just kind of have to jump in and start flinging equations around by trial and error until you bumble into the answer. But if you start writing, I mean, there aren't that many loops in this circuit. You start writing equations, and before very long, you should get this one. Here's the picture that goes with it. You've got 5-volt battery and got 15 ohms and 25 ohms. And I named the currents like this. What's coming out of the battery I called I3, and what's coming from the other battery I called I2, and what's going down the middle here I called I1, and I think I saw people that called this one I3, and there's no difference. These are just arbitrary names. So if you start here and start going around this loop that I've drawn, first thing you get to is the battery, at least if you go around counterclockwise, which, as I said the other day, doesn't make any difference. You can just as easily follow the loop in the other direction. But if you do it this way, you go from the low side to the high side. So that's a gain of 5 volts. And then, come down here, these two terms will both be negative because the loop takes you from the upstream end to the downstream end, so the potential is decreasing. Each of those voltages is given by Ohm's law. So I times R, the current through those resistors is I1. And this equation has only one variable in it. The variable happens to be the thing we're looking for. I didn't draw the ammeter in here because an ideal measuring instrument of any sort, whether it's measuring current or something's speed or anything else, an ideal measuring instrument does not alter the thing that it's trying to measure in the process of measuring it. And what that means in this case is that ideally an ammeter has no resistance. And so it acts just like a piece of wire. It's just unlike the other wires, it knows how to talk to you and tell you how much current is going through it. But the ammeter that sits right there doesn't do anything that enters into my equation, so I didn't bother to include it in the picture. But the current through that meter would be the I1. So you just finish the math. 5 volts equals 40 times I1. I1 equals 5 over 40, 0.125 of an amp. So as I probably said the other day, the worst case scenario with problems like this is you end up with a system of 3 equations with 3 unknowns and have to get into, either the substitution method or the adding the equations together, or there's other ways of doing it that involve things like determinants. But yeah, this was not the worst case scenario. Just a couple lines, there's the answer. Trick was to see if you were comfortable enough with the concepts here to spot that. Because if you know what you're doing, this was a very easy problem. Okay, the last thing, oh, before I get to that, something that was in my email today, I wanted to pass it. And things like this come around every year. This particular email was from RIT, Rochester Institute of Technology. And they're trying to get people to apply for a summer research program that they have. I think in their case, it's targeted specifically at community college students. I remember seeing the same thing last year, so this is at least the second year they've run it, but I should mention it's not just RIT. There are programs like this one all over the country. You know, if you want to spend the summer in Hawaii, apply to one in Hawaii. I put some links to this. I don't know if you've ever poked around all the little obscure corners of my website, you know, where you go to look at the homework solutions. But I've got some links there about summer internships and other information like that. Geneseo is another place, SUNY Geneseo, where they have summer internships. This particular one up at RIT, they're going to be working on multi-messenger astrophysics, meaning, well, the multi-messenger is different types of signals coming from the. It's a big deal now that they've got these gravitational wave observatories operating, where you pick up the gravitational waves from a couple of neutron stars or a couple of black holes that are running into each other, and you try and correlate that with something you're seeing with radio telescopes and optical telescopes, and you learn different things from different types of radiation. That's the one at RIT. There's several other areas of research for the one over. We actually sent somebody to the one in Geneseo, was it 2 years ago or 3? Anyhow, these things are, I believe, typically 10 weeks. They typically pay a stipend of a few $1,000s, and you know, if you're into sciencey kinds of things to do, it's interesting. It looks good on a resume, and I would encourage anybody to apply, because you don't really have anything to lose except maybe a small chunk out of your ego if they reject you. But that just means they had more applicants than they had room for. It doesn't mean they necessarily think there's anything wrong with you. So I would encourage any. There's another program where instead of going to a university, you go to one of the national laboratories. We've had a couple students over the years do that sort of thing too. But anyhow, back to this. The last thing under section 5 is a few words about electrical safety. What I always like to say about this is that after you finish this course, you may or may not ever need to know anything about Kirchhoff's laws again, but unless you plan to live in a tent in the middle of Montana and live on, you know, squirrels and berries and things like that, you're probably going to be living around electricity, so it might be good if you had some feeling for the bad things it can do to you, so that you know how to make them not happen. So, first of all, as you're probably aware, one of the potential problems with electricity is it can burn down your house, which would be especially unfortunate if you were in it at the time, but it's kind of a bad thing in general. Well, there's a couple of different ways a fire can start, but one is if you overload the wires. As I believe I've already mentioned, anytime you have an electric current flowing through a resistor, power equals I squared times R. Heat is produced at a rate equal to I squared times R. So the bigger the current through a given resistance, the more heat is produced. And actually, it goes up rather steeply. You know, if you triple the current, you get 9 times as much heat per second. The wires in the walls have some resistance. And, you know, you try and shove 100 amps through there, you're going to have the insulation just dripping off into a smoking puddle, which would be a bad idea. Actually, you don't even want to let it get that far. You don't even want them, you know, getting hot enough to make the insulation get brittle or anything as it ages. So there's a maximum safe current where the heating is kept down to I mean, the wires will get a little warm, but it won't actually hurt anything. For household wiring, you're usually dealing either with 20 amp circuits or 15 amp circuits. 14 gauge wire is good for 15 amps, 12 gauge wire is good for 20 amps, and so on. The fatter the wire, the more current it can handle. Well, this is why you have circuit breakers in that box down in the basement. Or if you've got an older house that's kind of grandfathered in, maybe you've still got a fuse box. Either way, you need some way of automatically turning off a circuit immediately if there's an overload. If you're drawing more amps than the wires are supposed to be capable of safely handling, something has to immediately turn it off. And so that's what your breakers are for. They are no help at all with electrocution. Okay, if you've got a 15 amp circuit breaker, that's enough to kill probably a couple dozen people if you wired them into the circuit in the right way. That's for fire protection. Fires can start in other ways too, like if you've got a joint between two wires, like where a wire is attached to the side of an outlet or something. If you don't have the screw tight, and it can arc a little bit there where it's jumping across the gap. You don't want that either. So anyhow, aside from issues related to burning down your house, there's what if an electrical current actually passes through your body. Well, this can cause 2 distinct types of injury. First of all, if you become part of a circuit, you are a resistor. And everything I just said about I squared R heating now applies to you. So if the current is large enough, you get a burn. Not that much different than if you touch a hot stove, except from a stove, you get burned from the outside in, and this would be more like getting burned from the inside out. But, you know, it hurts like, oh, nothing hurts like a burn. It hurts like the dickens, and maybe you get a blister or a charred spot. But from ordinary house current, you should not get burns so severe that it's life-threatening. Now, yeah, well, I'll explain more about that, but the amps flowing through your body are what hurts you, yes. The extent of the injury or whether you get injured at all depends on how many amps are passing through you. So, yes, I remember where I was. The wires along the side of the road, 5,000 volts, something like that up on the poles, like if there's a storm and they come down, yeah, that's another matter entirely. That can burn you severely enough that, let's not talk about the details because they'd be kind of gruesome. But as far as household 120 volts, the main thing you want, I mean, obviously you want to avoid a painful experience, but the main thing to worry about, because that's the only really life and death issue, is the second item on the list, which has to do with the fact that electrical impulses are what make muscles contract, okay? If I decide to wiggle my finger, that's because a little electrical impulse passed down the nerve fiber from my brain to my finger. okay? Or, as some of you may be aware, back in the late 1700s, early 1800s, after Volta had discovered the battery, voltaic pile as they called it back then, somebody discovered, and I have no idea what prompted somebody to try this, but they discovered that if you hooked up some wires to a set of frog's legs, clearly dead because the rest of the frog is missing, you hook up these wires and you give them a jolt of electricity and it makes the legs kick. I mean, this is where the story of Frankenstein's monster came from, okay? That was like cutting edge science fiction at the time it was written. So electricity makes muscles contract. I got a shock once where I couldn't let go of the wires. That's not an experience that you want to try. It's like, I'd really like to let go of these wires. But point is, the same thing can happen to your heart. Your heart is just a muscle. It doesn't know it's supposed to beat. It gets little electrical impulses at regular intervals that make the muscle contract. And when it contracts, it squishes the blood down through the arteries, and that makes it flow around your body and keep you alive. Well, just as when a stronger electrical, I was sending out an impulse that said, let go of the wires, but there was a stronger impulse that overwhelmed that kept the muscles contracted. If the same thing happens in your heart, there's a stronger current coming from somewhere else that could send the heart into an improper rhythm or stop it entirely, and neither one's really something that's a good idea. So you need to primarily be concerned about currents flowing through the chest area. Yes.
You said that you were, in your words, sending a current to let go, but is it that, like, that current was that much stronger than anything your body could have produced? And, or is it something that just makes it harder for you to let go? Because I know that depending on the actual electrical current that's running through you, it can be harder than you can let go. But even a little one, even something that isn't strong enough to kill you, is there still a way for you to not be able to release?
If that had gone through, well, yeah, if that current that went through my hand had passed through my heart, I'd have probably had a serious problem.
Yeah, I can't word today.
Well,
I'm very sorry, but I guess the question I was having is, it takes a certain electrical charge or electrical current for you to actually open your hand and close it.
Well, let's see. Is it that I have to send a current, or more like I have to not send a current and the muscles relax?
Yeah,
that I think is probably what it is.
Yeah, because I can engage muscle to actually force open my hand against something. So maybe that's a question for a biology professor. I really don't.
Yeah. Well, we'll do this. I'll tell you to go talk to a biologist, and the biologist will tell you that it's a physics question and you should go talk to me.
No, consult the internet and probably get a lie, but that's okay.
Something about aliens, yeah.
Something about essential oils.
Yeah. But I believe the way it works is that if you apply a small current, it makes the muscles contract, and then if you turn that current off, then they relax again. Although that's a little quicker than what you'd expect from just relax. I don't know. It's something like that, though. Play around with what?
It's basically a little box that you pads, and you can put the pads anywhere on your body. Turn on, it sends electrical signal from one pad to the other. And this makes
Electrodes. It's so it's for some people want to exercise without physically moving.
Hey, my wife got something like that once, and she thought it was great. And she said, "Here, try that." And she stuck them on me, and I went, "Oh, take that thing off of me."
Yeah, I saw one that it's an ab thing, and it's in the shape of a six-pack. You stick it to you, and it just contracts those muscles, and it's basically like a shock collar. In a way.
Wasn't my idea of fun, and
No, it's horrible.
Why did they go up the
well, because it was not the best day I've ever had at work. It was the first year I was working here, and it was when we did that free fall lab, you know, with the spark timer. And I wasn't paying attention. I had the hot wire hooked up to the ground and the ground wire hooked up.
Yes. You told us that.
And so I was standing in front of about 20 people and I said, pull the plug, pull the plug. And somebody pulled the plug.
Oh my.
No. And the best part of it is one of the students, the vice president of finance's son was taking the course that year. So,
Oh, I'm sure the business
So like a hot-
finances is like, you're about to be a horrible burden on this school.
I think the title was dean back then. We've had title inflation over the years. People who used to be deans are now vice presidents. People who used to be assistant deans are now deans.
This is almost irrelevant, but should that ever happen to you and then somebody knows CPR and is able to actually revive you, do they get extra points?
We'll see how hard they press
Piggybacking
me.
off of, the previous question.
I should talk about what I'm supposed to be talking about here. I said something about the lungs there. Yeah, current will paralyze your lungs also. But the thing is, it takes several minutes for you to smother. And when you turn the current off, normal breathing usually returns. You can stop the heart in a very small number of seconds, and normal rhythm doesn't necessarily return when you turn the current off. Your brain is sensitive to electrical currents also, but that's usually not an issue because your brain's out here on the periphery. Not too many people usually stick their heads inside some sort of electrical device. And
What's this?
so the main issue is the heart, which jumping further down the page is where that thing about keeping one hand in your pocket comes in, or different books put it different ways. One hand in your pocket, one hand behind your back. The point is you don't go sticking them both where they could touch something that they shouldn't touch. So like if you're repairing some electrical device, there are still a few things people repair instead of throwing away. Some piece of medical equipment or something. You take off the panel and there's this big sticker with red letters 1.5 inches tall that says, be sure the device is unplugged before removing this panel. And you look at it and you say to yourself, how am I supposed to check the voltages and find the problem if I've got it unplugged? So you set the panel over there. Well, you've used these multimeters a number of times by now. You know how they work. There's 2 wires coming out of there. If you've got 1 wire in each hand and you're poking around in there like this, and maybe you accidentally have the one hand brushed up against the chassis of the thing, which is grounded, and you accidentally touch some high voltage connection with your other hand, you've created a path where current can flow up your arm, through your chest, and down the other arm to complete a circuit. Whereas if you took the 1 wire from the meter and just hooked it to the chassis with an alligator clip, so you're just poking around in there like this, you can still get a shock, okay? If I was to ask you a question on a test about this and you said, oh, so you don't get shocked, that's not true. But it'll just be a shock to your hand. And your hand is a lot more rugged than your heart. It takes maybe 1 amp or so to burn out, depending on how large of an area it's spread over. It kind of depends on the current density, actually. There's a dumb luck factor when you get a shock, but if the current flows right through your heart in just the right way, it's not that many milliamps that it takes to kill you. So a shock that wouldn't even leave a mark on you if you're poking around in there with 1 hand. If you're doing this kind of thing, you're dead. Yes.
I'm not going to be actually question, surprisingly. So we're talking about the fact that once you create that circuit with both of your hands, that's when it becomes impossible to let go, and that's when it kills you? Or is it just that creating a circuit?
Well, in that case I was talking about before, that was 35,000 volts, and you can get a pretty good wrap on it. See, you don't quite have to have a complete circuit with an alternating current because the electrons don't really go anywhere. So I was kind of acting like a capacitor in that case. And so in spite of the fact I was wearing probably wearing rubber-soled shoes, this was almost 40 years ago. I don't remember which shoes I had on that day, but I was still able to get a pretty good buzz off of that wire. Ordinary house current. I remember I was replacing an outlet once, and I had turned off. It's like, yeah, everything in this room's off. Thought I'd unscrewed the right fuse down in the fuse box, and I've got the job half or 3/4 done, and I'm turning one of the screws. It's like, wait a minute, did I just feel what I thought I felt? And I plugged the lamp in that outlet, and it came on. The thing was live. Apparently, everything in that room was on the same circuit except that outlet right there. Well, old houses kind of grow like that. I mean, somebody first put electricity into the house in probably 1910. They had a light bulb hanging from a wire in the kitchen, and then they added things one at a time after that, and so wherever the closest wire was to splice into,
It was awful back then.
That reminds me of computer. Everything is ridiculously cross-wired. The light switch to the fan in theater 1 is in the boys' bathroom. And the lights to the bathroom are in the closet next to
where is that?
So there's the light switch to the bathroom.
In what building though? Where?
The theater.
Oh, here?
No, in Warsaw.
Oh, in Warsaw. Okay. So this was built in 1990,
Not
but
that one,
yeah, the one in Warsaw is quite a bit older.
So, I mean, I was doing a little bit of macabre research some time ago, about, when people were first kind of bringing electricity into the home, and it was kind of a rich people thing to have. It would have basically a light bulb with an outlet thingy attached to it. You could basically just plug whatever the hell you wanted into it, and it would create what they described as a little Christmas tree of things that you could just charge up. So you could be sitting there with an overloaded socket that had a light bulb, an electric iron, a toaster, more lights, and your phone plugged into it, like your telephone. You could sit there, and up until almost very recently, it wasn't illegal to have these kinds of things. And so up into even sometimes the 60s and 70s, people were overloading these wires on top of their homes. These homes having been built such a long ass time ago that they were dry, brittle, old buildings that went up like a Christmas tree. And, so when I was learning about that, I was learning a lot about holy shit.
You're making me cringe up here because my wife decided she wanted a new fixture in the upstairs hallway. So last weekend I was putting it in. And so I'm up in there, and my house is old enough, you can still see the fittings where some of the gas lights were before the house had electricity. And so I get the old thing out, and it's like every time I bend one of the wires, the insulation goes crack. It's like,
oh yeah.
It's like there's a section right there where that's just bare wire. I better get some. I taped it up and I try to put it back together and kind of.
At that point, I'm calling an electrician and I'm just throwing money at the problem because I don't.
Well,
really
they'd have to throw a lot of money at. We're talking punching holes in walls.
No,
and
I
things.
understand. I don't want to die.
Yeah, well, one of these days I'll get it taken care of. But for right now, I just put a lot of electrical tape
Just
on it.
look up like YouTube tutorial.
Anyhow, let's finish this off before it gets to be next Tuesday. So as we were saying earlier, the amount of injury depends on the amount of current flowing through your body, both in terms of if you get a burn, I squared times R, or also in terms of stopping your heart. There's a certain minimum threshold, a few microamps aren't going to hurt you any. There's a certain minimum amount of amps, or actually probably milliamps, involved in interfering with the rhythm of your heart or lungs or anything like that. So then if it's the amps that hurts you, why is it that people, including me, go around saying, don't touch that, that's high voltage, or, oh, under the hood of a car, 12 volts, that's not going to hurt you. It's because you are a resistor. So here's Ohm's law one more time. Your body has a certain amount of resistance. If you compare a car to a house, 10 times as many volts means 10 times as many amps going through you. Or if it's the wires along the side of the road up in the thousands of volts, that means that much more amps going through you. So high voltages are dangerous because they can push high amounts of current through you, usually. Now, something like, I think I've mentioned already in here, a static charge. Like I've got Van de Graaff's electrostatic generators in the back that can produce, on a good day, probably 50,000 volts. Why aren't there dead bodies laying all around the physics lab? Because it's, a little bit of static charge is not capable of producing any significant amount of amps. Each individual electron carries a lot of energy. That's why it's a high voltage. But there are very few electrons. You touch the thing and the voltage drops to zero pretty much immediately. And in the meantime, only microamps or something like that goes through you. So it's the current that does the damage, but high voltages generally are dangerous because they can push the amps through you. Now, a little bit of a footnote to that, most of the resistance of your body is in the skin. Your body is probably, it varies. If you perspire a lot, your resistance is going to go down. But on a typical day, you can measure it yourself this afternoon if you want. Just stick a couple of wires in one of those meters, set it for ohms, hold one wire in each hand, and you'll probably find your body's a couple 100,000 ohms at least. But that's almost entirely in the skin. If something was to happen, for example, where you got stabbed, then a voltage that would normally be nothing to worry about could suddenly become much more dangerous. Precautions. Many devices are grounded. A ground is a wire that leads to a stake driven into the ground, as in the earth is a huge reservoir of electric charge, at least if you get a few feet below the surface to where it's always kind of damp. You can dump charge into it, you can suck charge out of it. A wire that leads to ground is an alternate path for electric current to follow, so that if something goes wrong, the current follows that path instead of it going through you. On the other hand, it's very bad for you to be grounded, okay? Because a ground is a path for current to follow, and if that path is you, that's the whole thing you're trying to avoid. So not only one hand in a pocket, but like, don't go poking around in the fuse box in the basement if it's a damp earth floor and you're in your bare feet, because you can make a path, current comes up your arm, goes through your chest and down through your legs. You need that. Electricity will not flow if it has nowhere to flow to. And so if there's any chance something's a live wire, even though you think you've turned it off, you want to be sure you're isolated from any kind of a ground or any way of completing a circuit. The classic question, and I think it's in the homework somewhere, is about birds sitting on, the high voltage wires along the side of a road. I mean, you don't see dead birds lining the side of the road, because every time they land on the wire, the little smoking bird drops to the ground. The current has to have some place to flow to, or it doesn't. I mean, there's some insulation on the wires too, but even if there's a bare spot, maybe the bird gets a little tickle off of it, but that's about all. See, be careful you are not grounded. Keep one hand in your pocket. And in the event you see somebody else being shocked, it's the same advice they give lifeguards. The victim needs help, not company. So you have to treat that person as a live wire. Pull the plug and turn the device off that's shocking them, or if that's not possible, find some insulating object to knock them away or knock the wires out of their hands or something like that. Okay, well, I've got 10 minutes anyhow to start section 6. I was hoping for a little bit more than that, but I guess we had kind of a good discussion, which is worth something. Section 6 is pretty much just the same one thing over and over again. Different variations on the same idea. Because past experience has been that this is something we need to go through kind of slowly, because this is not just another week where we have some new equations to throw numbers at. Because, throwing numbers at one equation, you throw numbers at them all, right? It's kind of the same general skill, but this is supposed to be a calculus-based course after all. So let's have an application of integration here. You've got continuously distributed charge. Like the first example is about a charged thread or a charged rod or something like that. I guess I called it a rod in the question. And what is the electric field, a distance d to the left of that rod? Well, we've done some questions kind of like this before. Back in the unit on Gauss's law, you've got some charge distributed this way, find the electric field. You've got some charge distributed the other way, what's the electric field near that? Gauss's law is the basic equation of electrostatics, but it's only a useful problem-solving tool in situations that are very symmetrical, okay? In other words, you can use it when there's a nice Gaussian surface where the strength of the electric field and the angle between the electric field and the area vector, if that's the same all over the surface, then it becomes a very straightforward calculation. There are only a few very symmetrical types of situations where that's the case. An alternative that's better in some other cases is to consider, well, for example, what I'm going to do in number 1 here, that charged rod. We consider it to be a bunch of little point-like charges all lined up right next to each other. Each, you divide it up into infinitesimal pieces. The field from each of those infinitesimal pieces is given by the expression from section 1, Coulomb's law constant times Q over R squared. And then you apply the superposition principle. Add up the field of all of those little pieces to get the total for the entire rod, which, to phrase it another way, you integrate from one end of the rod to the other, okay? So that's pretty much the idea that we'll just repeatedly use for this whole assignment here. Let me try and at least get through the first example. I made things into like a 6-step check or 4-step checklist, do this and then do that and then do the other thing. So step 1 is to write down the field of one typical little piece of the charged object. There's the x-axis, and right there is a typical example of one of these little pieces I was talking about. We'll call its length dx. It's located a distance x from the origin because, you know, it's on the x-axis. So what's the x coordinate of the point where it's located? And I'll label what it is. It's a small piece. When I take the limit of infinitely many, infinitely small pieces, that piece will be a point charge, just like when I was talking about an electron the first week. So you can use the same formula for its field that I had the first week. What it says on your formula sheet under section 1 is that the field of a point-like charge is the Coulomb's law constant times Q over R squared. Well, the charge Q is this infinitesimal charge dQ in this case. And as far as the distance, you could call it R, you could call it X, it doesn't make any difference. I called it X because it's on the X-axis, but if you like R, call it R. For an electric field vector, you need to stick a direction on there. In these types of problems, I mentioned this before, when it's all just letters, no specific numbers, what you do is you assume the object to be positively charged. And if you actually, you know, when you're done, if you apply the result to something that's actually negatively charged, it's okay. Putting in a minus, you know, negative number for Q will just turn things around, and that'll take care of that. So if we're thinking of this as positively charged rod, electric fields point away from positive charges. So the field at the origin pointing away from this little charge here, that means it would point to the left. So to give it a direction, I stick minus I on there for my unit vector. Okay, so that's step 1. Divide it into point-like pieces, write down the field of one piece. Before you can integrate, you got to have everything in terms of the same variable. Well, I got an x, Coulomb's law constant and the unit vector, they're constants, but the q and the x, we've got to have it all in terms of the same variable. Generally, the way you get the substitution is in terms of the charge density. In this case, it's just a line of charge So you'd be talking about the charge per unit length. So this was step 1. This is step 2. The question says it's uniformly charged. There it is, uniformly charged. That means the charge per unit length for any part of the rod is the same as the charge per unit length for the entire rod. Capital Q, what I mean by that is the charge of the entire rod. Well, it says that in the question. Charge Q is uniformly distributed along the rod. L is the length of the entire rod. So charge of the whole rod, length of the whole rod. On the other side of the equals, charge of my little tiny piece, length of my little tiny piece. So charge per unit length for that little bit equals charge per unit length for the whole thing, uniformly charged. So therefore, rearranging dq equals q over L. Both of them are constants, times dx. Step 3, any other substitutions that are necessary? In this case, no other substitutions are necessary. That thing's ready to integrate. So 3, skip it. In this case, there's nothing to do there. To get E, the field of the entire rod, add up the, forgot my little arrow, add up the fields of all of the little pieces of the rods. Starting at the one end of the rod, the left end of the rod is at x equals d. The right hand end of the rod is at x equals d plus L. So that's going to be the integral of dx over x squared with a bunch of constants sitting there attached to it. And I will write out the details of that next time. I imagine there's people starting to drum their fingers out there. He was supposed to shut up 3 minutes ago. So this is the idea, anyhow. Doing this sort of thing is what Unit 6 is about. And I'll finish off the mathematical details of this one and do a few other examples next time.